All right, so with this next one, we have an arrow that's fired straight upward from a height of y naught with a velocity of v naught, and it lands on a cliff that is a height y above the archer. So we want to get an expression, derive an expression for time that'll be in the air. And then we're going to have the v naught, g, y naught, and y as a final answer. So if we sketch this problem out, what we have is we have a level ground here, and we have someone that is firing a bow, right? And it's going to go up some distance, and it's going to land on some cliff that is a height, a final position of y. Now it starts at this y naught, and it has an initial velocity v naught. So what do we know? Well, we can use the fourth kinematics equation that the change in vertical position is v naught t plus 1/2 at squared. Now, if you're starting to think like, all right, well, this is no longer 0. So how can I get time by itself? So I'm going to do a little bit of algebra here. I'm going to subtract the delta y, and that leaves 0 on the left-hand side. And I'm going to rearrange things a little bit. So I'm going to leave it as 1/2 of a times t squared plus v naught t. And actually, this a is really g, the acceleration of gravity, and then subtract my change in position. So you've encountered this in math class, that you have your basic format for a quadratic equation, and we have, your quadratic equation, right, follows 0 equals ax squared plus bx plus c. So this 1/2 of g becomes my a, the v naught becomes my b, and my minus my change in position becomes my c. And so if you think of the quadratic equation being that, your x is equal to minus b plus or minus the square root of b squared minus 4ac all over 2a, what we can do is we could plug in our b, right? That's our b, this is our a, and this is our c, in for that, and then that is our answer. So the time is equal to minus b, so minus v naught, plus or minus the square root of b squared, so v naught squared, minus 4 times a, which is 1/2 of g, so I'll write it 1/2 of g, and I'm going to simplify this a little bit, times c, which is minus my change in position, and then that's all over 2 times my a, which is 1/2 of g. All right, so cleaning this up a little bit, what we have here is, notice the minus and the minus, so I have minus v naught plus or minus the square root v naught squared, so that's nothing changes there, but I have a minus times a minus, so that becomes a positive. I have 4 times 1/2, so that's 2, times g, times my change in vertical position, and that is over 2 times 1/2, which is just 1, so it's g. Now, what will end up happening is that, remember kind of in math class, that if you have your basic quadratic, one of your roots is positive and one of your roots is negative. So when you go through with time, remember time is what we're solving for, the positive root is going to be the one that we're after. The negative root doesn't have any physical meaning. So if we have numbers in a situation like this, and you get 2 answers, one of those answers will be positive and one of those answers will be negative, and you just disregard the negative answer because that doesn't make conceptual sense. So that's it. No need to simplify it. All right, so the next one is definitely a multi-step problem. We have a rocket that's accelerating upward at rest from 3.2 Gs until it runs out of fuel at an altitude of 1,200 meters. After this point, it's in free fall, meaning that it continues going. So we're going to break it up into 2 parts. We're going to break it up into the part that the rocket is accelerating. Okay, so that goes up to an altitude of 1,200 meters. All right, so we have 2 problems. So for the first problem, our v naught is 0. The acceleration is 3.2 Gs, which is 3.2 times 9.8. And then our vertical distance is 1,200 meters. And we don't know two things. We don't know how long it takes to get there, and we also don't know how fast it's going at that vertical height. So it's going to be accelerating up until this point, but then from that point on, all right, so the second half, it's going to continue moving up and then come back down. So this is a whole separate problem. What we know here is the acceleration is negative 9.8 meters per second per second. We know the final speed, the speed at the top of this, when it reaches its maximum height, is 0. We don't know the initial speed, the speed at which it's going at that altitude, which we're going to figure out down here. But whatever that value is down here, we're going to plug in there. And then we also don't know the time. Okay, so there are three things that we're solving for, and we're going to put the two times together. So we're going to first figure out how long it takes to get to that 1,200 meters. And it doesn't have to be in this order. There's another order that you could do this in. Then we're going to figure out how fast it's going at that altitude. And then we're going to figure out, this is a more familiar problem, if you toss something up at some speed, how long does it take to stop? All right, so let's kind of break that down and do the time first. So to get the time, what we do know is that we know the vertical distance, we know the initial speed, and we know the acceleration. So our fourth equation, delta y equals v naught t plus 1/2 at squared. The v naught is 0. So 0 times any time is 0. And if I do a little bit of algebra, I multiply both sides by 2. Divide by a, that cancels that out. Divide by a, and then square root. So the time is equal to the square root of 2 times 1,200 divided by 3.2g, so that's 3.2 times 9.8. That's a 9. All right, and so I got a time there of 8.75 seconds. So that is how long it takes to get to that altitude. So in order to figure out how long then it takes to stop, what I need to know is how fast is it going at that altitude. So that second problem, what I'm going to do is, now that I know the time, I can do v equals v naught plus at. Okay? And once again, for this first half, the initial velocity is 0, and then I get the acceleration times the time. So this is 3.2 g's, so 3.2 times 9.8 times my time of 8.75 seconds. And so that gets me a vertical speed at the end at 1,200 meters to be 274.3 meters per second. Okay. So, all right, so we got step 1, we got step 2, now we got to get the third step to figure out the time. And fortunately, it is going to be the same scenario. I now know this is 274.3. I know its final velocity, and now it's in free fall. So now the acceleration is the negative 9.8 meters per second. And then I'm looking for time. So I get v equals v naught plus at. My final velocity is 0. I'm going to subtract my v naught over, and that equals at, and then divide by a. So my time is equal to the minus my initial velocity, which is the 274.3, over the negative 9.8 meters per second squared. And so that time works out to be 27.99. And then I take this time, this is the slowing down time, this is the speeding up time, and add the two to get a total time of the given value of 36.7 seconds. 36.7 seconds. All right. And then the last one, figuring out its maximum height. What I'm going to do, I'm going to use a little trick here. I already know how high it was going those first 8.75 seconds. That was 1,200 meters. So really what I'm going to do is just figure out how much further it goes up from there and then add the 1,200. This ends up being a pretty easy calculation once you have all the numbers above. So I'm going to use the vertical height. That's what I'm looking for. It's the initial velocity. That is the velocity, since I'm starting my problem at 1,200 meters, that is the velocity at 1,200 meters. That's a 274.3. So 274.3. I'm going to multiply that by the time that it's slowing down, so the 27.99. And then add 1/2 of negative 9.8 times my time, 27.99 seconds squared. And if you do the math here, I got to 3 sig figs, 3840 meters. And then, as I said, that this is going to be how much further it goes up from the 1,200. So then, in order to get the maximum height, I add the 1,200 meters to get the total of 5040. So, those of you that were in the first period, Caleb, it is 5040. Have a good night, guys.